Thank you very much. My name is Frank McQuillan from Pivotal. Really a pleasure to be here to speak to you about this very interesting topic of predictive maintenance and connected vehicles. My focus is going to be more on the platform, on the back-end platform. So I'd like to start with a quote from the head of after-sales analytics and digital processing at BMW, who says that the primary goal at the moment is predictive analytics. Being able to detect defects at the earliest stage. We have to find the right correlation patterns and incoming data to predict upcoming malfunctions and their consequences. So this is not an academic problem, and it's not a problem of the future when we have autonomous vehicles. It's a problem right now that car makers are working on and trying to solve for, because it's important to their business, it's important to the safety of their customers. This is not specific to vehicles on the road either. At Pivotal, we've had the privilege of working on other sorts of projects in transport, in trains, in ships, and in the past I've worked on drone-related projects. So this is very applicable to a wide range of projects. So I'm going to start with three truisms, or perhaps opinions, I suppose, on this topic. And the first is that this is a system design problem, right? So we want to come up with an architecture. We want to figure out what components go in that architecture. We want to figure out how these components fit together. We want to know what data we're dealing with, and we want to know what service level agreements we're signing up for. Right? So you could say, well, this is a classic system design problem. Well, the thing is, this is a very hard system design problem. And you could say that my colleagues on the data science side are being very unreasonable for all the things they're asking for, right? They're asking for a platform that's going to connect to multiple data sources of disparate types. They want to ingest that data. As that data is streaming in, they want to do operations on that data at high speed. Right? And these might not be just simple operations. This might be more complicated operations involving joining data with, streaming data with reference data, for example. They want to land that data in a data lake so that they can do data exploration with it and build their models. And then they want to deploy applications into the cloud in a way that can consume these models. Right, so it's a pretty tall order. And I'm actually very glad that this meetup is set up and that it's oriented towards data engineering, because open source gets a lot of glory, but it's how these components get put together that we can solve really practical problems. So open source is the starting point for sure. However, I would say that it is just the starting point, because it's unlikely that you're going to be able to go out and find a single open source project that's going to meet all of your needs to build a really practical system. I think over time we'll find out that you need to put together fewer of these open source projects, and that connectivity will improve. But there's no doubt in my mind that right now you're going to spend a lot of time looking at different open source projects in order to choose the best ones that are appropriate for you. There's tons of them out there. Of course, people know about the Apache Software Foundation, which is a really great place for like-minded developers to come together and build these products. That's a great place to go. There's other places in which you can go to find out what's going on in the open source space related to things that are interesting for predictive analytics. My third opinion is that there's no single best design. My colleagues showed a reference architecture that we've used at Pivotal here for some projects. That may not be the best reference architecture for you. However, I would say that there is an acceptable design. There is an acceptable system that you will be able to put together to solve for your problem, unless your requirements are unreasonable. But assuming that they are not, you can practically build something. So that was about my truisms. Let's talk a little bit more about the specifics of the platform. So what I've put up here is a starting point that kind of we looked at when we were thinking about system design for predictive maintenance of vehicles. So we want to connect to different devices, to different data sources, right? Oh, and by the way, when I say platform, I'm talking about a back-end platform. So I'm not talking about in-vehicle platforms. That might be an interesting topic for another meetup. But this platform that I'm talking about is once the data is from the vehicle into the back-end system, then how do we operate on it? That's sort of the focus of the platform that I'm talking about. So it needs to connect to multiple data sources. You need to ingest the data. You need to do streaming analytics on that data. You need to write it to some sort of big data store, which could be a Hadoop file system, it could be enterprise data warehouse. It could be an object store like AWS S3. Then you need tools for data exploration. So for doing data exploration, the kind of work that Esther and Watson were talking about, and then not only exploring the data, but then being able to build the models and then score the models. And finally, with respect to applications, you need to have a platform, a cloud-based platform that you can deploy these applications to and manage them in the cloud. So you want to operationalize these models, and you want to do it in a scale-out architecture in the cloud. So this is the reference architecture that was shown before. My focus is, we could spend a lot of time talking about this. I was going to focus on these sort of three areas, which are really principal areas of this architecture. So one is the data store in which the data is landed as it streams in. So as it streams in, it's landed into some kind of data lake or enterprise data warehouse. I'd like to talk a little bit about this because this is how models are built. And then I want to talk a little bit about the real-time components, Spring Cloud Data Flow and Apache Geode. Okay. Right, so starting with Apache Hawk. So Apache Hawk, the commercial name for this product is Pivotal HDB. And Apache Hawk is a Apache native SQL on Hadoop project, right? So we have our data in this data lake. A standard kind of workload for enterprise today is SQL, and it's because a lot of enterprises have invested huge amounts of energy into SQL. They've built up all kinds of queries that they use. They have people trained in SQL. It's very familiar. So if you land data in a data lake from your connected car, and then you offer the ability to do SQL queries at scale on that data, then that can be very attractive to folks. So just a little bit about the history of Hawk, and I think the reason I think this is relevant is that technologies like Hawk and Greenplum database are extremely complex, and they have fairly long pedigrees. In particular, this reaches back to the mid-'80s at UC Berkeley when Michael Stonebreaker developed the first Postgres database. Right, so around the mid-2005, Postgres was forked at 8.2, and that became Greenplum database. So what the team at Greenplum did is add this massively parallel processing capability to Postgres, and that became Greenplum. And from that, in 2012, then the characteristics of that MPP engine were ported to Hadoop, right? So it's the same massively parallel processing capability, but instead of on local storage, it's now in the Hadoop file system. And all of these products are open source now, Hawk, Greenplum, and Madlib. But I show you that to kind of give you a sense of where this product comes from. So I want to tell you a little bit about some of the kind of interesting things about Hawk. The first is around advanced analytics performance. So it's really been designed to work very well for complex queries and advanced analytics at scale. And this really comes by virtue of this massively parallel processing architecture. Another thing which is very important is SQL completeness, right? So this is by virtue of its pedigree with Postgres, that both Greenplum database and Apache Hawk are 100% SQL compliant. So they will run all of the queries in the standard benchmarks that people use to compare SQL engines. One of the ones that we use is something called TPCDS. And TPCDS is a set of queries which are in the area of kind of OLAP, data mining, analytics. So you want to ensure that you're using, if you're using SQL, you're using a SQL product that supports kind of all of the standard queries that people use. The third thing here is around integrated machine learning, which I'll talk about in a bit. Elasticity is very important in Hawk. A key thing about elasticity is that it scales both by within a query. So this is one of the new interesting things in Hawk 2.0 is that it uses this idea of virtual segments. So the query processor actually can figure out how to parallelize a query on the fly, and it will do different kinds of parallelization depending on the query. So that's one feature of elasticity in Hawk. And finally, it has a very advanced query optimizer. A query optimizer is the thing that takes a SQL query and turns it into an execution plan, right? So Hawk is really the first cost-based optimizer for big data. Right, so that's one characteristic. That's one of the components that we use in this reference architecture. I just wanted to show you something on performance because not only is scalability is important, but performance is extremely important. So this is a comparison benchmark we did with Impala in the fall. And it uses this benchmark that I mentioned called TPCDS. And it consists of about 99 queries. So Hawk is able to run all of these queries, and Impala was able to complete 62 of them, right? So about 2/3 of them. Of the ones that it completed, this chart shows the difference in execution time, right? So for the 62 queries that completed, on the y-axis, the green up shows the particular queries in which Hawk was faster and by how much. And the negative y-axis is the queries in which Impala was faster. So in general, over the full set of these 62 queries, Hawk was about 4.5 times faster. So performance is important. Connectivity is important as well, right? So we want to connect all of these components together, but how do you do that? So one way to do that in the Greenplum database and the Hawk world is to use something called PXF. So PXF stands for Hawk Extension Framework. And this is a way that enables Hawk to connect to other non-native formats, right? And to do so in an efficient way. So here it's showing connectivity to HBase and to Hive. And by efficient, what I mean is that it doesn't just copy the data into Hawk native format and query it. It uses this idea of push down predicates, where it takes certain aspects of the query, pushes it down into the target system, runs it there, and just gets result sets back. Right? So when you're thinking about putting these systems together, think about not only the performance and scalability of the components, but how they will interact with other components in your framework. So Apache MADLib. Apache MADLib is a scalable in-database machine learning library. It's open source, and It runs on Postgres, on Greenplum database, and also on Apache Hawk. And the two kind of key things about, well, first I'll start with this idea of in database. So what does in database mean? You don't want to, in your system, be moving large chunks of data around, right? So you want to bring the computation to where the data is. So the idea about in-database machine learning, and this came from work that Joe Hellerstein did at UC Berkeley about 5 or 6 years ago, was how can you, in an MPP architecture, in a massively parallel processing architecture, take machine learning to data in the different segments, right? So that's this idea of bringing computation to the data. MATLib has a full set of libraries. There's something in the order of 35 to 40 principal algorithms that our data science colleagues use. And it spans kind of the standard supervised learning to unsupervised learning, as well as a bunch of statistical methods and utility methods for operating on data. All right, so the features of MATLib are parallelism. It's really hard to take a machine learning algorithm and make it distributed. That's sort of an art and science of itself, and there's a team here at Pivotal that works on that. And there's also an associated community, the MATLib community, who works on that. So parallelism, scalability, making sure those things scale so that as your data size increases, you don't need to change your software. And we aim for linear or sublinear scalability generally with data size. Better predictive accuracy means you don't need to sample your data. You can use all of your data. Okay, so we're talking about this area here, which was sort of the batch world. Let's move to the streaming world now. So Spring Cloud Data Flow. Spring Cloud Data Flow Okay, so Spring Cloud Data Flow is the cloud native version of Spring XD, so Spring Cloud Data Flow is now, there's now a release candidate up, and it will GA probably within the next month or so. And the idea behind Spring Cloud Data Flow is that developers can create and orchestrate data pipelines for common use cases such as data ingestion, analytics, etc. So you can think of Spring Cloud Data Flow as a way to glue a lot of these systems in your reference architecture together, right? There are other products out there that projects out there that can do similar things. And so there's a bunch of options there. We're very fond of the Spring project, so we're using Spring Cloud Data Flow in this reference architecture. So here's an example. You want to define a stream. It's very simple. You define, in this case, an HTTP source. You're going to do some transformation on that data. And then you're going to sync it to some sort of sync, or send the result of that to some kind of sync. Right, so interaction with Spring Cloud Data Flow is very simple. There's a drag and drop UI. There's command line interface. You can curl to a URL. And it also supports a wide variety of runtimes. So this is something to think about when you're designing a system, is like, what are the runtimes that you're going to be using? The interesting thing with Spring Cloud Data Flow, it supports Cloud Foundry, it supports Kubernetes, it supports Apache Mesos, supports Yarn, and you can run it locally as well, right? So you have a wide variety of options with respect to runtimes for Spring Cloud Data Flow. Just in the interest of time, I'll skip ahead a little bit. Ecosystem is important. So when you're looking at components, make sure that you don't fall in love with something in isolation that's not connectable to the rest of the world, or that makes it very hard for you to connect to the rest of the world. An interesting thing about the Spring ecosystem is that it is so vast. There are so many Spring projects that you can take advantage of. For example, Spring Data is one, right? We have all these connectors. We want to talk to Gemfire or to Apache Geode. Spring has a connector. Spring Data has a connector for that. If you want to talk to Spark or Spark Streaming, Spring Cloud Dataflow can talk to Spark or Spark Streaming. There's existing connections for those, robust connections. So think about the ecosystem associated with the components that you select. So we talked about sort of gluing these components together with Spring Cloud Dataflow. Let's talk about Apache Geode now. So this is when we get into sort of the really enterprise grade capability of the system that you're going to build. Apache Geode, the commercial name of it is Pivotal Gemfire. And Gemfire, as some folks in the room may know, has been around for a very long time. It's got hundreds of customers in automotive, in government, in financial services, very strong in financial services. It's an in-memory distributed database. It has very strong consistency, and it's built to support low-level transactional applications at very, very large scale, right? So I guess the key kind of characteristics of Gemfire then are latency and scale, right? So there's different topologies in which Apache Geode is used. In the case of our connected car or our connected vehicle reference architecture, I think the key things here are the horizontal scalability, right? So if you're doing operations in memory on very, very large data sets, then the horizontal scalability is key. And one example we were talking about is if you have data streams coming in, and then you're joining that data with very large reference data, right? Because you want to put that together as features to input into a model, to scoring of a machine learning model. And you have, tens of millions of cars out there sending you data, then that horizontal scalability is really key, right? You can run a lot of POCs, and we've done that without Geode in the loop, but once you want to operationalize at scale, then products like this are very interesting. I'll point out maybe one more thing, which is integration with analytical databases, right? So in our architecture, we had a linkage between this fast layer and the enterprise data warehouse, right? So what Apache Geode allows you to do is have a very high-speed connection between that fast layer and your batch layer. Like many vendors, this is something that actually guys need to think about. Folks need to think about when you're putting these open source components together. Are you going to just go to the GitHub repos and download stuff from there? Are you actually going to go with a vendor who is packaging these things? So Pivotal, like other vendors, packages open source products that we sell to our customers. So we have something called the Big Data Suite, which packages Greenplum Database, Pivotal HDB based on Hawk, and Pivotal Gemfire, which is based on Geode. So then for enterprise customers, they're not just using open source software, right? They want a vendor to stand behind it. I wanted to say something about other architectures. Like I showed you one that has worked for us, but that might not work for you. So I just picked a couple examples I want to show you, which I'm not going to go into detail, but I'm just going to flash them by. This is kind of to demonstrate that you can put these systems together with other pieces. This is a very interesting presentation. If you have time, go to Berlin Buzzwords Conference from about a month ago in Berlin. There was somebody who presented on predictive maintenance for SNCF, so the train system in France. And these are the components that she talked about. They're using NiFi, they're using Spark, using Elasticsearch, and she talks about how they put those together for their architecture. This is an IoT services architecture from Azure. This is just from their white paper or something. You can see they mention predictive maintenance. They have a lot of the kind of key ideas that we talked about before. They have streaming stuff coming in here. They have data stores here. They have complex event processing and rules engine, which is operating on streaming data. And they have machine learning. In this case, their Azure ML product in the for their public cloud. This is a partner of ours, GE. They have a platform called Predix. And Predix is, they call it the Industrial Internet Platform, which is used for a wide variety of use cases, including predictive maintenance. It includes data capture, processing, and management. It's also built on Cloud Foundry, which we didn't have a lot of time to talk about today, which is a platform as a service that we build all of our applications on and we deploy a lot of our systems into. And this is our old friend, the Lambda architecture, which you've probably seen before. This is an architecture, a sort of template, which divides the world into a batch layer, a speed layer, and a serving layer in between. What I found kind of looking around at these architectures after a while is I very soon ended up in this world of boxology, where you had all these boxes that people put up. And as a data engineer, when you're trying to build a system, this can kind of inform you, I suppose. For myself, I'm actually not particularly crazy about this because it seems to be leaving so much out. And this may not work for me. This might not work for you. But it seems like it's kind of the devil is in the details in actually building these systems out. So I want to finish on challenges. I'll just take a couple minutes to talk about this. So with respect to challenges in building these systems, there are many. I think the first one is managing complexity. You saw that if you want to build a practical system that really scales and that works well, there's a lot of pieces that you need to put together. So complexity is really a challenge and something that we've struggled with. Integration is a challenge. How do these components talk to each other? That really make you think about working on something that's in an ecosystem in which people working in the open source are very interested in connecting components together. If you're left to connecting the components together yourself, then you're going to have a heck of a lot of work to do. Open source, how to choose, how to keep up. Data security and lineage. This is obvious, the data security from the point of view of privacy, because this system knows where you go, when you go there and what your route is to get there, but also from the point of view of, danger, right? If a system like this is doing push notifications into the vehicle and that gets hacked, then you're in danger of things like cognitive overload for drivers who are getting information which is confusing to them, and that can present a hazard. IT and car development cycles are not in sync. It takes like 3 to 5 years to design and build and manufacture and bring a car to market. Here at Pivotal, we're all about agile. We like to push new releases like once a week. So think about the difference between an IT department who wants to update stuff all the time and the whole mechanism and the machinery of building a new car. For guys across the street like Tesla, they thought about this from the beginning. But from the legacy or the traditional car makers, this is a challenge. These departments in the past have not talked to each other. There's multiple vendors involved. Car makers are going to need to be partnering with mobile partners. That's going to inform the standards and things they use and what you put into your platforms. Car dealers need to connect to the platform. This is sort of talked about earlier. If I'm at like Lake Tahoe and I get a push notification that my transmission needs servicing and it vectors me to a dealer, that's great. But when I get to that dealer, they need to know I'm coming. When I come, they need to scan my VIN and have like full situational awareness about what's the problem with my vehicle, what is the history on my vehicle, repair history, as well as all the information associated with similar repairs on other vehicles. So they need to be plugged into this system. And where does that leave the poor corner garage? That's where I got to fix my 15-year-old Volvo. Those guys are not going to be connected to this platform, right? So there's going to be really a change in the servicing world for connected vehicles in the future. We talked about who will pay for connected car services. I think the final one I want to mention is fleet management. There's a lot of really interesting things in fleet management that can be done here. Because think about all the data that's in this platform now. For a fleet provider, you can then look at scheduling your repairs so they're done in such a way to minimize the impact on your customers, right? And also, you can consider the state of your vehicles in your route planning, right? You don't want to, as soon as there's a problem with a vehicle, immediately send it back to base or send it for repairs. If it's a minor issue, they may be able to continue doing some of their deliveries, and therefore that would be more cost effective for yourself. So integrating maintenance within the route planning can be very interesting. In the past, I've worked on projects in drones like that, but it's probably going to come to vehicles as well. So finally, I would say it's a hard system design problem, but looking around the room at all of these smart people and curious people, it's certainly a system design problem that you can solve. Thank you very much.